Hey there! In this video, we're going to reinvent game physics from scratch. I believe that the best way to understand something is not to look at the complex thing that exists now, but to go back to square one and try to go step by step through the process of inventing that complex thing. So game physics can be daunting, and physics in general, but in fact it's actually quite simple, and it kind of follows from the very real and very simple problems that you encounter when you try to invent something like this. By the end of this video, you'll be able to build your own physics engine in Dart. Now, I'm not saying that you should make a physics engine from scratch. I don't think that there's too few physics engines in the world, but you'll be able to do it. And also, sometimes, actually quite often, games need physics that are custom made for them, right? So there are definitely games that Angry Birds that need physics engines that can do everything. But for every Angry Birds game, there's a lot of other games that actually only need very simple physics, and you don't need to have like a full physics engine to run them. Actually, it would get in your way if you had a full physics engine. So by the end of the video, you'll be able to understand what game developers mean when they say things like delta time or velocity vector. And you'll also be able and understand what it means to do Euler's numerical integration, which sounds fancy, but it's actually really simple. Spoiler alert. All right, let's get to it. It's possible that you have a preconceived notion of what physics are, and that comes from schooling, right? Like in high school, we get problems in physics like how far will this car go given the acceleration, blah, 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 or, where will these trains meet, and all that stuff, right? Well, game physics is actually different and in many ways much simpler, because all game physics needs to find out is what happens next. And the next is not like in an hour, but it's in the next frame. So in 1/60th of a second, 120th of the second, it's a very short time. So, and for that, it turns out that very simple maths can get you a long way. So say that we have this cannonball here, half hidden, hopefully not for long, and we want it to go from left to right, right? So in Flutter, you could just do it with an animation, right? And in other places as well, you could just say like, okay, so there's an animation, it will be this duration, and we will just change the X coordinate of this cannonball through that animation from this to this, right? That works, except we want to simulate things because at some point we don't know what's going to happen. The player could jump in the face of the cannonball and then it should not go further, right? There could be another cannonball that bumps into this one. There could be a number of things. Also, things will get more complicated in the future. It's not going to be just going from left to right. There might be gravity, there might be explosions that affect the behavior of the cannonball. So we can't use a preconceived animation. We need to go frame by frame. So how do we do that? Well, we need to run a function every frame to get to know what happens next, right? And this is called a game loop. And every game that has physics in it needs a game loop that runs every frame, right? So how do we do that? Well, we're not going to go into details about game loops. Many places, like for example, if you're using Flame as your game engine inside Flutter, then Flame gives you a game loop in itself. So you just kind of hook up to your objects to it. but it could be something as simple as what I have here is I have a widget, and that widget has a animation controller. Then I can just start running the controller with repeat, so it goes forever. And then every time that controller fires, or basically every frame, then I update the world. So you don't need to really look at this code. That's why I put it elsewhere than what we'll be looking at now. I just wanted to let you know what's happening in the background. It's a simple function that gets called, that calls our world every frame and tells our world, hey, do your physics update. Figure out what happens next in this frame. So how do we make the cannonball to go from left to right? Well, the easiest thing that we can do is just add every frame, add to the x coordinate of the ball, right? So that should be easy. So we have ball x equals ball x plus 1, right? Or plus equals would also work, of course. I just want to make it completely clear. Well, like we're in this new frame, ball will be 1 point to the right compared to the last frame. That's it, right? And so if we run it, sure enough, the ball goes to the right, which is cool. And the reason, this obviously the thing that it resets to the left is something that I put into my game widget here, just so that we don't need to deal with that, and I can like keep showing this to you. So obviously we would have to program it normally, but here we just talk about physics. So we're going to just look at this this ball going from left to right, right? So this is actually exactly what I have programmed in step 2. Ball x equals ball x plus 1. There's a problem though. This function, the update function, is called every single frame. So what happens if you have a different refresh rate? Well, if you, for example, run this on a 120 hertz screen, then everything will be faster. If you run it on a, I don't know, 90 hertz screen, it will be 50% faster than right here, because this monitor goes 60 hertz, as far as I know, right? So if we go on a 120 screen, it's like doing this, just like running it twice in the span of our 60 hertz frame. And you obviously don't want this in your games. Like imagine that people with 120 hertz screens would have their game twice faster than anyone else. So we need to address that, obviously. All right, so the way that games deal with this is by using a different kind of update function. Instead of just being called with no arguments, games get an update function that gives them an argument called delta time, dt, very often just called dt, but it stands for delta time. And this argument delta time says how long has it been since the last update function. So on a 60 hertz screen, this will be 1/60th of a second. On a 120 hertz screen, this will be 1/120th of a second, right? So in that case, we can use this number to kind of scale the amount of movement and an amount of everything, forces and everything that gets applied to our objects in the game, right? So let's switch to step 3, and right now we just have +1, right? But we could do +1 times dt, which means we want to scale the speed by the refresh rate, basically, right? And now I've saved and hot reloaded, and you can see it's very slow. This is because now we're not doing 1 pixel per frame, we're doing 1 pixel per second, right? Because dt is 1/60th of a second, right? or whatever the refresh rate is. This is cool because now instead of just like some weird one number, we have a physical unit, right? Like it's 1 pixel or 1 unit of distance per second, which gets us back to physics, right? And so we can, of course, change the speed, right? So it could be like 100. And we have a speed of 100 pixels per second, and it's great, and it's going to look the same on any device regardless of refresh rate. We can obviously extract this number to be, I don't know, here, and then use it here, and now we have this exact thing, which is basically ball x equals ball x plus speed times delta time. Right? I want to note that this variable delta time has its problem in physics computations, but we'll ignore that for now and we'll get back to it by the end of the video, I swear. Okay, so we can move our cannonball to the right. I think it's obvious that you could also do it to the left or up and down, right? But what if we want to move our cannonball to any direction, right? So like north, northeast or whatever. Well, for that, we could still go with what we have here, right? Like we could have a speed in the x direction, and then we could have another different speed for the y direction, and then just do 2 of these. But a much better approach that also scales much better with complexity is using vectors. So that's basically, instead of having a position as 2 doubles, x and y, we have this class called vector2 that has x and y in it already, right? So this vector2 comes from vector math, which is a package that is, by the way, also used by Flutter itself. It's, I think, I'm pretty sure, I'm 100% sure that it is maintained by the Flutter team. And this is basically all it does. It has like a way to express 2 numbers in one as a vector. Now, I don't want to go into like a depth of like what vectors are, but yeah, basically that's what they are. They are 2 numbers. And if you have a vector like this means that there is 0 in the x direction and 100 in the y direction. And then if you have a vector like this is speed in the x direction and 0 in the y direction. So this should do exactly the same thing as before, except now we are using vector math. Now, as a Flutter developer, you could be more familiar with offset, which is basically the same thing. You have a class that has 2 numbers in it, dx and dy, and you can do things like, you know, plus and minus, and you can scale them and all that. The only reason we are using vector2 and not offset is that vector is more performant than an offset. It's actually a mutable value. It's a little more low level, but for a game of almost any reasonable size, it will be better than using offsets. So now we're still going just in the cardinal direction, but hopefully you can see that it will be very easy for us to change this to something else, right? So this could be like, I don't know, 10 times dt, and then suddenly our cannonball goes downwards. And if that's the case, then of course, instead of just doing like 2 numbers, then our velocity should also be a vector, right? So I'm doing var velocity is a vector that is 100 in the right direction and I don't know, 20 in the down direction, right? We don't need speed anymore. And instead of doing this, we can just say velocity times dt, because you can actually multiply a vector by a scalar value. dt is a scalar value, meaning it's just one, number. And that will just scale both of these numbers by dt, which is what you would expect, right? So now we have a nice way to express the velocity of the cannonball as a vector. We also have the position of the cannonball as a vector, and all is back to simple stuff. Now, the reason we call it velocity is that velocity is a vector, speed is a scalar. So the magnitude of the vector, so like velocity length, is speed, right? So this is again from physics. Like if someone asks you, hey, what's the speed of this ball? Then it's not a vector, it's a number, like, I don't know, 30 miles per hour. But if someone is asking you what the velocity is, that's where the vector comes in, because it encodes both the size, but most importantly, it's also which direction. Now, the next step is to realize that the velocity here is actually not something that belongs to the world, which is like this kind of class that we are using to update the state of the world, but it belongs to the cannonball itself, right? The ball has a velocity. So instead of doing it like this, where we somehow figure it out in the world, we can just put the velocity into the cannonball object itself. And so now we have position and velocity both as fields in cannonball. So just to summarize this whole vector thing, why do we use vectors? Well, first of all, it's readability. Instead of x and y, we have position. Instead of speed x, speed y, we have velocity, or vx, vy, we have velocity. It's just one thing that encompasses the whole idea of velocity and position, right? We get all this functionality from vector math, which is to say we can we can add and multiply and dot product vectors between each other, and we can apply matrices, so we can rotate things. We get the magnitude, so there's a bunch of things that we get kind of for free by just using vector math. And I can't not mention the performance angle, right? So the vector 2 is actually made to be performant. We're not really using that here, and I don't think we have the time to actually go into like how to rewrite this into being more performant. But suffice it to say, vector 2 gives you the ability to not create new instances of vector every time that you change something. This is the main this is the main change or main difference from offset, which whenever you add offset to an offset, you create a new offset, which is memory pressure, and then instead with vectors you can be like, okay, change this position vector in place, which is very cheap for the computer, and you don't allocate more memory. So anyway, yeah, vector 2 is great. Use it if you have anything 2D in your game. All right, so we have this cannonball going in a straight line, but let's be honest, straight lines are boring. We want things to curve and, act more naturally. And for that, we need acceleration in some form or another. So from physics, you probably remember that acceleration is a change of velocity over time, the same way that velocity is a change of position over time. which should give you the idea of what we're going to do next, right? So I think it's step number 7. Yep. So we still do position is position plus velocity, but then we add a new element into the mix, another vector 2, another vector, and that vector goes from this mouse position vector, which is where we have our mouse, to actually it goes from the position, because we have a subtraction here. So we're basically saying take the position of the mouse wherever it is, and then subtract the position of the ball wherever it is, and what you get from that is like the direction from wherever the ball is towards wherever the mouse is currently. Right? And so we have our acceleration towards the mouse, and it's going to be bigger if the mouse is further away and smaller if the mouse is closer to the cannonball. And then what we do is exactly the same thing as with position here, and that's velocity is velocity plus acceleration times dt. Still using the delta time, obviously, because, yeah. So yeah, if you go to step 7, you can see that now the cannonball follows my mouse around. Actually, it kind of like orbits the mouse if I do it this way. But I can kind of you can think of it either as what's it called, like a rubber band. Or it could, of course, be something from space, like, I'm the sun here with my mouse, and this is the Earth or something else, right? But you can you already see kind of a physics going on here with just the two things. The position is updated by velocity times delta time, and the velocity is updated by the acceleration by delta time. And it's just 2 lines of code, really, right? So this right here, what you see, the position equals position plus velocity times dt, and velocity equals velocity plus acceleration times dt, this is called explicit Euler integration. So it was invented by Euler, I don't know, a couple of hundreds years ago. So it's a pretty old thing, but it works, right? The only problem is that we can't see it here, but it can get kind of out of whack after a while. The better thing that most game engines use instead is called semi-implicit Euler. And don't ask me to explain what exactly that means. But basically what it is that in the update method, instead of doing first position and then velocity, we just do this. First velocity and then position. So we update the velocity with the acceleration and with the position from like the last frame first. And then we use that new velocity, newly updated velocity, to update the position. Before it was like this, and this could this could cause little errors in our computation. It's still not going to be, of course, this is explicit, like numerical integration. So there's always going to be numerical different like little errors. And it's not going to be as precise as if we used some like other integration method, but it's good enough for most games out there. So, whoa, yes. So this is not what I meant by the small errors. This is actually us having like a very long delta time and see what it does. Yeah, because we had I went to a different window, and so the next delta time, the next frame was many seconds after the last one, And so things just get really, really out of whack. But thankfully, it's not a big deal, because normally you have control over saying like, okay, so we never go too far with the delta time, right? And we'll get back to time step later. So anyway, you can see the difference really, but step 7 was the implicit Euler, explicit Euler integration. This one is the semi-implicit Euler, and both are very similar and good enough. All right, so we had our fun with following the mouse around and all that, but obviously the acceleration can go in any direction, and often it goes down, and we're talking about acceleration due to gravity. So instead of like using mouse position or anything like that, we can just do vector to 0 and I don't know, 20, and then hopefully, yeah, we just go down, right? Like you'd expect with gravity. So let's say if we add in step 9, we have the same thing. We have acceleration due to gravity, but the initial velocity of our ball is going to the right. And so we have this where it almost looks like a normal cannonball, right? Just kind of going to the right and kind of going down as well. And but then going through the ground, which is not what we want. So let's talk about collisions. A big reason to have physics in games is collisions. Collisions often mean that something hits something else, right? So it means that you hit someone, or maybe you landed on the platform that you tried to hit, or you tried to jump to, and so on and so forth. So collisions are important. We're not going to go like too deeply into like how exactly you implement collisions, because this could be very different for very different games. But for something like here, for something very simple, it's obvious. We have a ground, which is also like kind of the lower boundary of our world. And so what we can do is as simple as this. If the ball position plus half of its size is bigger than the height of the world, we're talking about the world here, then let's set the position to exactly there. Like, so the kind of, if it goes below the ground, put it on the ground, and then set the velocity in the y direction to 0. So right now you can see what it does. Step 10 goes down and then resets the velocity, doesn't reset the x velocity, and just keeps sliding on the ground, right? So this can be one collision, and how to do it. So how about colliding with something else? Well, we're not going to go into details, but basically what you do is you check every object in your game with every other object in your game, and you see if they collide, right? So with a ball and a different ball, it could be just as easy as finding out how close they are, and then if that closeness is smaller than the radii of the balls, then they are in contact and they collided, right? And then you do something with the collision. You could one of them could explode, both of them could go into different directions, whatever your game needs, right? It gets more complicated with things like polygons, rectangles, whatever. Then you have to figure out, okay, so do the polygons overlap in some way? On the other end of the spectrum, if you talk about platformers, then in platformers you generally have everything is like a rectangle, and it's an axis aligned rectangle. So it has like a top X, top Y, and bottom, I mean, you know, this piece and this piece, and it's axis aligned, it's not rotated. And so it's pretty easy if you have two axis aligned rectangles to figure out if they overlap or not. And so like if you have a character like Mario and a platform, then it's pretty easy to figure out if Mario is not on the platform, on top of the platform, below, and so on and so forth, right? Now, admittedly, this doesn't really look like physics at all, because I don't think any material in the world would come to complete, vertical stop like this. So we can do it a little more interesting by saying, okay, everything else is the same, except the velocity y is not 0 anymore, but it's half of the previous velocity. So the velocity or speed with which the ball is going down, we half it and invert it. So it should do like this. We're in step 11. So let's see. And of course, you can totally tweak the number and like how much of the velocity comes back. So it could be something like, if we make it very high, it will just keep jumping like a gum or rubber band ball. If we make it very small, like this, then it will be almost like before. Maybe something like this. Almost like before, but yeah. Did you see that? That's more like a cannonball, I think. Anyway, so yeah, that's collisions. All right, so we talked about position, velocity, acceleration. Now we have to talk about forces. If you remember your physics, you probably know that physics are a big deal. I mean, the forces are a big deal in physics. And the equation that we care about is that acceleration equals force divided by mass, right? So you can have a force like a jetpack, for example, and then it depends on the mass of the object that the force is acting upon to see how the force accelerates the object, how much it accelerates the object, right? So again, like let's say we have a jetpack, the same jetpack with the same force of its jets, right? You attach it to someone like me, like 100-kilogram person, then the jetpack will struggle to actually get me up from the ground. Like the acceleration will be pretty slow, maybe even too slow to lift me, right? If you put the same jetpack on a kid who's like half my mass and half my weight, then the kid will be it will just go up because the same force was acting on mass that is half of mine, right? So that's the only thing that you need to know about forces. I think the most obvious force that acts upon a cannonball is gravity, right? But gravity is already implemented. We've already implemented it as acceleration, and it actually isn't interesting to add gravity as a force instead of just acceleration, because with gravity, the mass cancels out, right? So I thought long and hard about like what other force can act on a cannonball that's not gravity, and it needs to be a continuous force, right? And I didn't really come up with anything clever because we'll be talking about air drag later. So all I have is silly, and it's magnetism. So imagine that there's like a big magnet here, and it acts on the cannonball from here. And so here's what it looks like. We have magnetic force, which goes to the left, right? And then the acceleration due to the magnetic force is magnetic force divided by mass. Again, magnetic force is a vector and mass is just a number that we added to the cannonball, right? And we can tweak it, of course. And then we also have gravitational acceleration. We just keep it that way. And then the final acceleration is this plus this, right? And then the rest is exactly the same as before. So this is step 12. Let's see it. So we go down with gravity, but also the big magnet on the left is pulling the ball to the left. All right. So you combine it like this. You can, of course, combine the forces together first and then compute the acceleration with something like this. Here, I just have it separate. So you have acceleration, gravitational acceleration, magnetic acceleration, and then I just plus them together. Normally, you'd have like a big one force, like a big vector here that says vector to forces that are applied on the object, or you gather them in some other way. Like, what are the forces that act on my object at this point? And then you would put them together, you would convert them to acceleration, and you would apply the acceleration to the velocity, and that's it. All right, next up is air drag, right? Like our cannonball is acting as if it was in a vacuum, just like there's no drag, there's no friction to it, which is generally not a good idea. Most games, even if they actually happen in space, have some kind of friction to them because that's what people expect, right? So we need to add friction, air drag, or whatever else. Maybe this could be in water, but you still have some kind of drag, right? So what we have is I got rid of the magnet. We have gravitational acceleration again, and then we have air drag. And ideally, the way that you could do it is with actual forces, right? So like you would find out what the force is giving the given the velocity and given the everything else, and then you would apply that force as every other force. But again, pragmatically, most games would just do something with the velocity. And in this case, it just like takes the velocity, it scales it to 30% of that, and then inverts it again, and then use that air drag as acceleration, and that's it, right? You could do this in many ways. You could do it the right way, the kind of the physics way. You could scale like this. You could just literally just like linearly remove or subtract from the velocity as you go along. This really depends on what you're trying to make as a game. So the last physics thing that I want to talk about is impulses. And impulses are similar to forces, except forces are applied continuously over long periods of time. Impulse is always at a moment, like it just like happens. A good impulse, for example, is when you kick a ball. That's generally modeled as an impulse, right? Of course, if you go slow enough, it's also a force, right? Because like your foot is starting to apply force to the ball, and then the ball starts to move and so on and so forth. But in practice, it's an impulse. It's like in one frame, everything happens. So impulses are everywhere in games, as you can imagine. Anytime anything it gets kicked or gets hit, or maybe there's like an explosion. So impulse is very similar to force. I have it here. So what I added is if I click anywhere with my mouse, first I find out what the impulse is. So I'll see where the position of the ball is. I subtract mouse position. I think this is the opposite of what we had before. So now it's like the vector, the resulting vector goes from the mouse towards the ball. Then I normalize it. See, this is how vector math helps us. Normalizing it just means that the vector, well, we don't care about the magnitude or the length of the vector. We just care about where it's looking, and it will always be a unit vector, meaning it's going to be a length of 1. Don't worry about it. And then we scale it by some number. And impulses generally are big numbers because they need to do a lot of stuff in one frame, right? And then how you apply impulse, how you apply an impulse is you literally just add it to velocity, but you add the impulse divided by mass again, like with the forces, right? So let's run this. This is step 14, and now I can apply impulses to the ball. I can actually, I think I can dribble, yeah, I can dribble with a cannonball, which is something that I do a lot in real life, of course. Cool. Anyway, so yeah, so this was the last one, impulse. There's obviously more physics that we could implement, right? But I think this is like a good point where this could be useful for many games, and I will get back to what other things you could imagine and add to your physics engine later. But right now, I think this is a good point to kind of pause and talk about terminology. Objects in physics simulations can be categorized into a few different categories. One of them is a rigid body, which is what we've been trying to implement here with the cannonball, right? So a rigid body is something whose motion is completely controlled by the whims of the physics. So forces, impulses, everything like that. The cannonball itself does not have any like scripted motions or anything. So that's a rigid body. Obviously, our cannonball is not a fully realized rigid body. There would be more to simulate in a proper physics engine, but it is a rigid body by at least one way of looking at it. But generally, in game simulation, you have more than just rigid bodies. You have static bodies, which is things like the ground, a wall. If you have a racing simulation, then the barriers on the racetrack, these do not move, and so therefore they're static. A step above static bodies is something we call kinematic bodies, or in Unreal Engine they call them movable. But anyway, these are objects that are controlled by special code that you write yourself. An example could be the player character often isn't really, given into the whims of the physics. You control him directly and you want tight control. So like when you press the left button, the character immediately goes to the left, or almost immediately. And you don't just like, apply some force to them or something like this. Another example is like moving platforms in Super Mario, or like these like cows that cross your road in Super Mario Kart, the character, and so on and so forth, right? So these are kinematic bodies. Then there's the rigid bodies that we talked about, and that are basically like fully simulated in physics. They are called dynamic bodies in Unity and GameMaker. And in Unreal, they're called physics objects, just so you know. But yeah, we call them rigid bodies, and like Bug Studio calls them rigid bodies. And yeah, these are projectiles. They are, rockets with jet engines attached. Anything that is like really fully. Even in Angry Birds, the birds are rigid objects. Pigs in Angry Birds are also rigid bodies. And then everything else in Angry Birds, except maybe the ground, is a rigid body because you can interact with it through the physics engine. And then some games have something called soft bodies, which is objects that can change shape. So ropes is one example. Goo and cloth and slime is another thing that changes shape, but it can still be physically simulated. There are things like destructible walls. In some games, they are made as soft bodies. In others, there are other ways to do it. And then there are whole genres which use destructible vehicles that are simulated as soft bodies. And while we're at it, we should also mention particle-based fluids like water or lava. And while these are not in most games, there are some games that kind of like are based on the fact that they can simulate fluids. Like, for example, I remember a game called Where's My Water, where you basically solve puzzles with water. But yeah, these are not very often simulated. So there you have it. You have static bodies, you have kinematic bodies, you have rigid bodies, you have soft bodies, and you have fluids. And we mostly talked about rigid bodies, but you can imagine is close to what you would be doing with a kinematic body as well. Maybe you just like forego all the forces and just use velocity immediately and stuff like this, right? So yeah, and then of course static bodies are pretty easy. You just put them and they stay there the whole game. Now, we obviously haven't covered the whole problem space of physics in games, right? But I try to figure out what are the most important basics. And I think whatever game you'll try to implement, you will probably use maybe like 60, 70, 80% of what we talked about here. And then for your particular game, you will have to learn more. For example, maybe you are trying to build a car racer, right? Then you should probably look into cornering forces, which is how a car stays on track, right? It's not skidding all the time, but it goes like that into corners, right? Maybe you should look into angular forces or angular speed and momentum and so on and so forth, which is what happens when things rotate, right? So again, like Super Mario doesn't need angular forces, but if you have something like Angry Birds or the car that rotates by driving around, then you need angular forces and an angular momentum and angular speed. You should also understand the difference between particles and objects in games. So we talked about rigid bodies and all these things. In many games, you also, for graphical effects, you want particles. Particles are generally way more lightweight than game objects. They are also more short-lived, so like they will exist for half a second, for example. And that these could be sparks and like puffs of smoke and so on and so forth. And they are not physics simulated generally, or the physics applied to them is very simplified. They don't collide. Like if two puffs of smoke collide, nothing happens. They, sparks also don't collide, and they maybe have something like gravity applied to them, and some kind of like velocity and momentum applied to them. But that's it, and then they disappear, and all is fine. We also haven't talked about things like coyote time and other ways in which games generally cheat physics in order to make themselves more fun to the player, right? So, for example, coyote time is when you have a platformer and you generally have everything, like the physics are there, but in the platformer, you have the player kind of jump off a platform, right? But in the old times, it would be that like the player runs and then they try to jump at the very last second so that they can get to the next platform. But obviously with physics, if they miss the last second or last fraction of a second, then they are not anymore on the platform. They're in free air, right? So if they jump, it shouldn't matter. Like if you push jump here, then there should be nothing. You just like fall down to your death, right? But it turns out people find this very frustrating, right? So physics in platformers since like, I don't know, 20 years ago at least, have this thing called coyote time, which is named after Coyote from the Warner Brothers cartoon. And they will just let you jump even if you're in midair. Midair, that's what I was going to say. So if the game engine or if the physics engine detects that you are just like 2 milliseconds or 2 frames before you were on a platform and now you're not, and now you're jumping, it will say, yeah, let him jump. and it just works. And so like if you watch these games in slow motion, you will sometimes see that the main character will just like jump from here. That's just one example. There are hundreds more examples, and you would be surprised how much and for how long games have been doing this. And so don't get too enamored or too in love with physics and with the realism and the precision of the physics, and instead think about how to make the game more fun, right? So that's Coyote time. We don't have time to really go into all of the ways that you can do it, but you can learn more elsewhere. Another interesting topic that we don't really have time for, at least not in this video, is the whole deal with time step and the fact that if you have delta time that gets large enough, your whole physics engine can go out of whack. And this actually happens quite a lot. Like if you've ever played a game and then maybe it was a racing game and suddenly one of the cars kind of jump into space, or someone ran through the wall, this is often somehow connected with time steps. And so for now, I'll leave in the description, I'll leave a link to an article that tells you what to do with these things. It's called Fix Your Time Step. But yeah, it's a thing. For many games, it doesn't really matter. But for many other games, it does matter. So, but yeah, we're not going to talk about it now. I should also point out, if you want to have a game that is fully physics-based, like most of the things in the game are actually rigid bodies, and you want all the rigid bodies to respond to like angular momentum and to all of this, then you probably don't want to build your own physics engine. In Dart, we have Box2D, which is a library that is, I think, originally in C, written in C, but it has been ported to many other languages, including Dart, and it is well maintained. I think it is pretty, and it has very decent performance, much better than what I would be able to do here, and it supports everything that you might want to have, right? So if you have something like this, if you have a game idea that is based on physics, just use Box2D. I still think it's nice to be able to understand what's going on in the physics engine, but it's better to use something that's already there and that has been maintained for many years. Now you might be asking, so, well, why don't everyone just use Box2D when it's already out there? Well, the thing is, most games don't really need that, and it would actually, like, they will lose control over the gameplay if they just simulate everything in box 2D. So that's why most games don't do it. For example, like if you have something like Super Mario, you obviously don't want Super Mario to be a rigid body, because then anytime he bumps his head on anything, he will start rotating and then you have to deal with the rotation and so on and so forth. No, you just want like a very simple, well, actually it's pretty complex, but it's not physics based. It's something else. It's a kinematic object. And you often want to have something in the middle, and you want to have it custom, and you want to have it based on the fun of the game and not necessarily on being a precise rigid body simulation. So that's why you probably don't want to use box 2D. Another thing that I didn't talk about was 3D, right? But so I kind of assumed that we're talking about 2D. Obviously, physics works in 3D as well as in 2D. The good news is that what we talked about basically can be very easily transferable to 3D. So, position instead of vector 2 is vector 3 with 3 numbers. Velocity and acceleration, all of these are just same thing. They are vectors, except they're in space, right? Things get more complicated with things like rotation in 3D. You probably want to use something called quaternions, which don't ask me how. It's pretty, advanced stuff. But yeah, it's like if you understand the basics in 2D, you're very, very close to understanding the basics in 3D as well. All right, so I hope that this video helped demystify game physics for you. I hope that you now understand that game physics is actually just things like position plus equals speed times delta time, and that's it. So it's nothing scary, and it just works, and you can do it yourself, or you can do just half of it yourself, or you can use something like Box 2D. Always remember that when implementing physics in a game, that it's more about the game than about the physics. So if you have something that maybe violates a physical law or two, but is actually fun, then it should go in. It's like, what are you talking about? It's not about making the most realistic physics simulation. It's about making an awesome game. So do that. And this, what we talked about, is all about that. And now you know how exactly the physics work, and so that you can say, okay, you know what? I don't actually want impulses to be this or that. Like you have all the control over how exactly the physics in your game work. And let me tell you, most games that you've ever played don't actually have realistic physics in any way or kind. What you're used to in games is not realism, it's game physics. And feel free to modify and to tweak physics in the service of fun. That's all I wanted to say. Thanks for watching.